There we go. There we go. All right. So thanks for having me here. It's a great time to be part of a ITAMP workshop. This is actually my first one of these such workshops. So maybe I'll continue to come to them. I'm here to sort of bridge the gap perhaps between the morning of talks having to do with cold atom or atomic cavity QED and maybe circuits, which is what I do now. So we're going to talk about some of these topics, but mostly about quantum circuits in this talk. And before I run out of time at the end of the talk, I want to acknowledge the students in my lab who actually do the work in the lab most of the time. So I'll talk about work from a third-year graduate student, Patrick Harrington, and a second-year graduate student, Jonathan Monroe. And then Matthew Nagalu is the senior student in my group who sort of makes everything happen. But most of his focus is on topics that I won't cover today, because I'm trying to actually talk about things that have, in some sense, a relationship to many-body cavity QED. So lots of things here have to do with single atom, single mode physics, which shouldn't be addressed here. So start with a bit of a historical perspective. In 2004, I was already felt like I was working on my PhD in Dan Stepper Kern's group for quite some time. We were trying to make a system where we put atoms into between two very high finesse mirrors to enter this regime of strong coupling, cavity QED. And this wonderful paper came out from Yale, from Andreas Walraff, where they were able to just basically blow the parameter regime we were interested in out of the water. So the coupling is so much stronger than anything we could hope to achieve, which was really encouraging as a second-year graduate student. And throughout the years, the Yale group and many other groups have really pioneered cavity QED with superconducting qubits, taking it into regimes that are really phenomenal, so such as the dispersive strong coupling regime. This allows us to resolve single photon states in the cavity and various things like that. And now they're doing very nice work controlling the states of light in a single cavity with these superconducting circuits, creating a whole sort of new way to do quantum computation with Schrodinger cat states in these microwave cavities. So a lot of nice work. I would say the circuit QED community, so it's a take on the name cavity QED because we use circuits instead, allows new regimes of cavity QED. We're very good at single atom cavity QED. And as I was on the airplane, scratching my head thinking about what are some examples in the circuit QED community where we have many-body physics. So I started thinking about, well, what are some examples of n greater than 1 body circuit QED experiments? So here's just an incomplete list of some things just to advertise to the cold atom community some of the sort of things we're doing in circuit QED. So there's an experiment from Leo DiCarlo's group at Delft where they have two qubits, so two atoms in a cavity, and they can make a joint measurement of the parity of these two qubits and thereby entangle these two qubits. So there's a very nice experiment. There's a nice experiment from Andreas Walraff's group from a couple of years ago where they studied this classic phenomenon of Dicke superradiance. Again, a sort of minimal case of this with two atoms in a cavity, but it's a very nice experiment. There's an experiment from Irfan Siddiqui's group at Berkeley where now they've stepped it up to 3 atoms. We have a Bose-Hubbard chain consisting of 3 of these artificial atoms. And they were able to do some very nice bath engineering experiments with this system. So you can see we're increasing in complexity, but they went back down to 2, so 1 atom and 1 cavity. Again, thinking about bath engineering, but working with more than just 1 qubit in a cavity. A couple more examples to highlight. Rajamani Vijayaraghovan's group at the Tata Institute for Fundamental Research in India has some nice experiments where they're taking 3 qubits and they wire them together so there's always-on pairwise longitudinal coupling. And you can actually extend this up to 10 qubits, 20 qubits. It gets very complex to control these things, but it's a way to create a qubit system where you have many qubits that are always highly interacting. So it's kind of they call it the trimon when there's just 3 qubits. And we'll hear, I just left this talk from Andrew Houck, and so I just wanted to mention some of the work in his group. I think is actually what he's going to talk about. I don't know if he's in this room. Yeah, maybe I got it right. So very nice work where really starting to truly explore many-body physics with cavity QED. So looking at dissipative phase transitions, stepping it up to lattices of 72 cavities with 72 qubits, so where n is getting much larger than 1. So we'll get to hear from him about that. So circuits are very good at the single atom cavity QED. We have this very strong coupling. We can work in a parameter regime where our cavities are much smaller than the wavelength of light that we're using. But it's challenging to work with many qubits to create n equals 10 to the 6 atoms in our system because of disorder, because we actually fabricate these systems. So our typical circuit we might study is this sort of transmon circuit. Involves a Josephson junction, which we draw as an X, and some sort of capacitor. And the problem is that these are man-made structures, and they're therefore thereby subject to disorder. So here's just an example. There's a very nice experiment from some folks at Chalmers where they're able to take one of these Josephson junctions, which is just a superconductor insulator, superconductor sandwich, and they were to slice it in half and look with TEM at that tunnel barrier. So there's aluminum oxide tunnel barrier, and measure the thickness distribution. And what they find is that it's not particularly uniform. It varies by, almost a whole nanometer. And because the tunneling current varies exponentially with the barrier thickness, this means that actually a very small area of this junction is participating in the tunneling. Okay, so the only knob we really have to change the Josephson energy and thereby tune the frequency of these artificial atoms is the area of this junction. And if only 10% of the junction is contributing, then it's very challenging to make uniform quantum systems. So that's the challenge we're up against. I'd say 1% variation is quite optimistic. So we're going to always be working with disordered systems if we're thinking about many atoms systems. Okay. So instead, I think the opportunities in circuit quantum electrodynamics for many-body physics really have to do with many electromagnetic modes. So here's a few experiments from last year. There were a number of experiments where they're exploring a regime of ultra-strong coupling. So one experiment where we have a flux qubit that's coupled to a continuum. So it's just a single atom coupled to a waveguide, and the coupling strength gets to the point where it is comparable with the frequency of the transition. Okay. And there's an example where a flux qubit is coupled to a cavity. Again, so in this deep, ultra-strong coupling regime where the coupling rate exceeds the other frequencies in the problem. And then another piece of research to highlight from Andrew Hauck's group is on the same year, they have a very nice experiment where they have a qubit coupled to a photonic crystal medium. So again, many electromagnetic modes participating at once. And the last thing I want to highlight is this work from Nico Rolk's group in Grenoble, where they use a metamaterial to explore ultra-strong coupling between an atom and many electromagnetic modes at once. So you can see here we have strong coupling to lots of different modes at the same time. So ultra-strong coupling to many modes. And so the take-home message, or the area I think our circuits can really contribute to many-body cavity QED is in a regime where we have a qubit interacting with many electromagnetic modes at the same time. And so in this talk, I want to tell you about a couple experiments one that we've done, one that we have we're just starting to work on, so it's a very preliminary set of ideas that harness the idea of single quantum system coupling to many electromagnetic modes. And what's different from that? What can you achieve with that that you can't achieve when you're talking about just a single qubit in a single mode? So the first part is going to be about the Zeno effect. So this will be the third talk in a row to use the name of this Greek philosopher, Zeno. We're going to talk about the Zeno effects, not so much xenodynamics, but I'll try to draw a connection between the two. So this is where measurement alters the coupling to the many modes of the electromagnetic environment. It's time to wake up, somebody. So that's the Zeno effects. That's something we did just last year. And then in the last bit of my talk, I'll talk about our recent experiments where we're exploring the physics of a qubit coupled to a microwave photonic waveguide, and show that we could, by harnessing the varying density states of the environment, allows us to study some bath engineering ideas and prepare non-trivial states of the system with dissipation. Okay, so the Zeno effect is named after the Zeno's arrow paradox. And Zeno said, hey, look, an arrow cannot move. And here's the reasoning. It's really not too complicated. Let's say we divide time into an infinite number of durationless points. Then at any given moment, an arrow has two options. It can either stay at location A, or it can move to location B. But it can't, so stay at A, move to B. But it can't stay at A because it's already there, and it can't move to point B because no time elapses. Therefore, no motion is possible. Okay, I don't know if that makes much sense. But in quantum mechanics, if the experts will oblige, the Zeno effect is best described in the context of Schrödinger's cat. That is, this is an experiment where you have a radioactive atom in a box, a pellet of poison of some sort, and you put a cat in this box. And the idea is that if we put a lid on the box and we check on the box every once in a while and find the cat alive, we reset the clock of the decay process, thereby initializing it back to the beginning and inhibiting the decay of the atom, keeping the cat alive. Okay? So this raises a couple questions. The first being, does measurement actually alter a decay rate of an atom? Is that even possible? And so let's start with that. And the answer is generally no, and here's why. If you think about the decay rate of an atom, it's given by a Fermi's golden rule argument, where we have this equation up here. So one of those terms is a transition matrix element. Okay, that's some integral you have to do. And the other term is the density of states at the appropriate energy. Okay, so if you think about the electromagnetic vacuum, we have a white density of states. And so what does the measurement do? So we have to look at what's the density of states at the relevant transition frequency. Okay, that tells us the decay rate. And if we think about opening the box repeatedly, what we do is we actually disturb the energy levels of our atom in some sense, thereby effectively allowing it to sample a broader density of states. But if we have a white density of states, then the effective average number of electromagnetic modes we couple to doesn't change. So we wouldn't expect that by repeatedly measuring some decaying system, we would change its decay rate. So we shouldn't expect to see these Zeno effects unless we happen to have some sort of upper frequency cutoff. That is, if you can imagine your atom has some finite extent, wavelengths that are much shorter than the size of your atom, maybe those don't really contribute to this argument. And so if you measure fast enough, you could reach a regime where the density state starts to roll off, and you'd expect, by measuring something frequently enough, you would inhibit the decay. Okay. But it turns out that for any reasonable parameters, this is an absurdly fast measurement rate. And many people claim that your thing will explode if you try to measure it that fast, or something like that. But the basic idea, maybe if we move away from just having a white density of states, is the following. So the Zeno effect would correspond to some case where by measuring and thereby sampling a larger range of frequencies, we reduce the density of states on average. That would thereby inhibit decay, reducing the decay rate. But you can see it's also possible to have the opposite effect, that is an anti-Zeno effect, where, say, if we're on the side here and we have a positive curvature, by measuring and therefore sampling a larger range of frequencies, we can increase the density of states on average, thereby enhancing decay. So the so-called anti-Zeno effect. Okay, so we were interested at first, somewhat just as a hobby, to go explore these two effects. In fact, Paul Kwiat suggested we just go measure this because he didn't know of anyone who'd done this experiment. And so we thought, okay, what does it take to study this Zeno effect? We need really two ingredients. One is a way to measure these systems. And so the way we'll do that is really the workhorse tool in circuit quantum electrodynamics, which is a dispersive sigma z measurement. Okay, so this is this dispersive interaction between our qubit, so here's our qubit energy, and the cavity. What we effectively get is a shift of the cavity frequency depending on the state of the qubit. Okay, so in order to measure the state of the qubit, what we simply do is we probe the cavity with some coherent light. Because the frequency of the cavity changes depending on the state of the qubit, we accrue either a positive or a negative phase shift depending on the state of the qubit. And therefore, by measuring what the phase shift we've achieved on the light, we can determine the state of the qubit. So this is sort of a workhorse technique in this field. The second ingredient we need is a peak density of states. So rather than changing the structure of boundary conditions in our system to create this sort of peak density of states, we're going to do something a little simpler and just create a thermal noise bath that's non-Markovian, that's sort of peaked at one frequency. And this is fairly simple to do. We just take some low frequency noise and we mix it up to the appropriate frequency of our qubit so that we end up with some sort of thermal bath, an environment to which this qubit couples, centered at a certain frequency, which we can tune around with this frequency. And we can characterize that in terms of a number of thermal photons in that bath. So what does this do? Well, the thermal photons, they induce simulated emission and absorption from the bath, and thereby enhancing the decay rate. So if we think about the decay time, the lifetime of the qubit, the T1 time, it's going to be reduced relative to its spontaneous emission lifetime by a factor related to the number of photons. And so this graph shows us that. This is our measured T1 time, something like 16 microseconds, when that's a typical spontaneous emission lifetime. And then as we change the detuning so that the qubit is resonant with the bath, we see an abrupt dip in the lifetime, meaning that we have more thermal photons, have stimulated emission, and the decay rate is effectively enhanced. Okay. So let's study the Zeno effects, seeing how the measurement affects the decay rate. So it's a very simple experiment. We just excite the qubit to its excited state, and then we're going to let it decay for some period of time before measuring what state it's in. But while it's decaying, we're actually going to pulse on, measurement pulses onto the cavity. These are brief 100 nanosecond duration pulses that effectively measure the state of the qubit and might inhibit its decay. Okay, so what I'll plot for you is the change in the lifetime of the qubit. So it's a lifetime with measurement minus lifetime without the measurement, normalized to the lifetime without measurement. So this is a fractional change in lifetime, and that's shown here. So what do we see? We see regions, okay, and then these two different colors indicate what the measurement rate is. So here, the blue one is where I apply this measurement pulse every microsecond. The green one's every 500 nanoseconds. And what we see is regions where the lifetime with measurement is much longer than it is without measurement. In fact, twice as long. And some regions where the lifetime is shorter with measurement, without measurement. So these are these Zeno and anti-Zeno effects. The Zeno effect is, of course, where the lifetime is longer. And that corresponds to the case where we're centered on the bath. And by measuring it, we allow it to sample, on average, fewer modes of the environment. And then we have regions where the decay is accelerated, and that's the case here where by measuring where it samples more modes of our thermal bath. Okay, so that's Zeno and anti-Zeno effects measured maybe for the first time on a single quantum system for what that's worth. But let's look a little deeper into this measurement interaction. And as I said, what it is it's a qubit state-dependent phase shift of a probe on the cavity. Okay, so I can write it down in this way, that I have a Hamiltonian that has this dispersive coupling rate chi. For a two-level system, this would be just g squared over delta, that dispersive coupling rate we've seen many times. But I could easily take this term, chi sigma z eta ray, and associate with the qubit frequency over here, in which case you can think of it as a photon number dependent frequency shift of the qubit. Okay, so there's really kind of two things going on. In one case, we can think of it as this qubit state-dependent frequency shift of the cavity. By measuring the phase of the transmitted light, we learn information about whether or not it's in its ground or its excited state, causing back action that's along a line of constant longitude of the Bloch sphere, pushing it toward the ground or excited state. On the other hand, if we were to measure the other quadrature of the field, that is the amplitude of this, that tells us about the number of photons that probe the cavity, telling us about how the frequency of the qubit evolved, telling us about whether or not it's how its frequency evolved, therefore causing it to precess on the equator of the Bloch sphere. So we have two different ways of looking at the measurement. One case we're learning about what state it's in. Another case we're causing dephasing on this coherent superposition. Okay, and with superconducting qubits, our technique for measuring the field actually allows us to select between these two different types of effects. That is, the type of measurement we make on the field is a phase-sensitive measurement, corresponds to squeezing of the electromagnetic field. So if we set up our amplifier to amplify the Q quadrature and de-amplify the I quadrature, this is just telling me about the phase shift of the system. Effectively, I have entangled my qubit with the field, and now I measure the field in a specific basis, that is, in the Q basis. And that corresponds to motion toward the ground or excited state, information about what state it's in. On the other hand, if I measure amplify the I quadrature and de-amplify the Q quadrature, I'll learn about what the amplitude of the field was, conveying information about what the photon number distribution in the cavity was, learning about what sort of phase the qubit acquired. So there's two different things going on, and we can, in principle, select between the two. And this just comes down to the fact that a quantum measurement is, you can entangle your quantum system with some quantum pointer state. We make measurements on that pointer state, and that gives different back action on the quantum system. Okay, so there's two types of back action. Which one of these is responsible for the Zeno effects? So in the talks earlier today, the discussion of the Zeno dynamics, which is very similar, had to do with the fact that you're projecting it back into initial state. So you might think that it really has to do with the type of back action that causes us tells us information about what state it's in. Another way to put that is the collapse part important to the Zeno effects, is the fact that you're looking in the box and projecting the system back onto its initial state. The essential physics of the Zeno effect, or does it have to do with the disturbance, that is this dephasing? Okay, so to explore that, we designed a test measurement that would try to disturb the system but collect no information. Here's how that works. It's something called a quasi-measurement, or this terminology was put forth by Franco Nori's group in 2013. And what they proposed is a simple experiment like this. You could apply a pi pulse when the qubit's in the excited state to a higher level state, and let it then radiatively decay back to the excited state. And it's a measurement because if you detect this photon, you know it's projected back into its excited state, but then you could think about what are the dynamics if you don't bother to detect this photon. But in principle, this measurement still accumulates information about what state it's in, even if we don't use that information. So our version of a quasi-measurement is the following. What we're going to do is we simply make a pi pulse to bring the qubit to the excited state, and then apply another pi pulse to bring it back down to the excited state. Okay? And all I'm going to do is I'm going to adjust the phase between these two pulses. And what this relative phase does, it actually imparts a Berry phase on the qubit. So it's going to acquire a geometric phase based on what type of rotations I do, bringing it up and down. So you can get a sense of what's going on by just a quick Ramsey measurement. For example, create a superposition, apply one of these quasi-measurements, and then close the Ramsey loop. And we see that what we see is an oscillation. So as we change this phase of this quasi-measurement, we go through a full 2 pi oscillation in a Ramsey measurement. So this is just this geometric phase applied by taking the qubit out of its manifold and back in with 2 different phase pulses. Okay, the idea behind the quasi-measurement is what I'm going to do is I'm going to randomize the second phase. So this will be some pseudo-random number generator that'll cause me to average over this all these possible phase shifts. And so this quasi-measurement only dephases the qubit, but acquires no information about what state it's in. That is, as long as these pulses are made with classical drives, there's no information obtained. It just disturbs, but doesn't learn anything. Not so useful, but for answering a question, it's useful. So the question is, when we apply these quasi-measurements, where there's no information accumulated, therefore not projecting it back into its initial state, do these Zeno effects still occur, or do they not? What do you think? They do. Dan thinks they do. Well, good. So what we're going to do is exactly that experiment, but now instead of actually measuring what state it's in, we'll just apply these quasi-measurement pulses. And lo and behold, you still see Zeno effects just like we saw before. So you see places where the decay is inhibited and the places where the decay is accelerated. Okay, so what this tells us is that it's not really something about the measurement collapse of the wave function. It's really the disturbance that causes these Zeno effects. And that's also true of these Zeno dynamics. It's the disturbance of of the energy levels, the erasing of coherence, that's really important, not something spooky about the information obtained. It all comes down to the spectrum of the qubit, that is the picture I showed you at the beginning. How does the qubit spectrum overlap with the density of states in some convolution? And so we can check on that just by looking at what the spectrum of the qubit is when applying these two different measurements. So here's just a typical spectroscopy trace. What we do is we apply a very weak drive to the qubit, and then we measure what the excitation probability is. And we can do that without applying any measurement. That's the black curve. So it's just slightly power-broadened spectrum of the qubit. And then we can apply these measurements at varying rates, at a rate of half a megahertz, 1 megahertz, 2 megahertz, and so forth and so on. And we see that as we measure it, we broaden the state. We also see some modulation from the fact that we're pulsing the measurement on and off. And we do the same thing with quasi-measurements. We see a very similar type of spectrum that we see dephasing and broadening in a very similar way. So it's really about the spectrum of the qubit and how we've changed that, not something funny about the measurement. So if you will oblige my silly video one more time, it all comes down to this Schrodinger's cat picture. That is, by checking on the cat periodically, you can either accelerate the decay, but if you find certain circumstances where you measure fast enough, you can actually accelerate the decay and cause the demise of the cat. But at the end of the day, it's not important to learn about whether the cat is alive or dead, and therefore the atom is decayed or not decayed. It's all you really need to do is shake the box. Yeah, like that. Okay. So thank you for obliging my videos. So I've showed you both these Zeno and anti-Zeno effects. And the point I want to make, or to draw into the context of this workshop, is that these are really examples of many-body effects in some sense, because it has to do with many electromagnetic modes and this changing density of states. I showed you these quasi-measurements, that the actual collapse of the wave function or information is not important. It's really disturbance. So you can imagine using these quasi-measurements now to create xenodynamics in a way that you don't actually have to measure what the state of the qubit is. Okay. So we can also do the state of the decay rate with measurement. And in the future, we're interested in extending this to non-thermal baths, so entangled baths and so forth, other structures, and also exploring xenodynamics in this sort of system. Okay. So with that, I'll move on to the sort of second part of the talk, which is thinking about a qubit coupled to a microwave photonic waveguide. So we can think about a microwave photonic crystal as some periodically modulated in the surfactant medium. And what this periodic modulation does is it changes our typical dispersion relationship so that we get both bands and gaps of allowed energies. And again, to continue highlighting Andrew Hauk's work, you're going to do my talk many times, apparently. They did some very nice work just last year where they studied a modulated impedance waveguide, and they coupled a single transbond qubit to this, and they could see some nice physics, such as a photon-bound state. It's characterized by a localization length. So if you look at what this actually looks like, we see this is the transmission through the system. So blue is low transmission, red is high transmission, and we see a region where there's a band and a region where there's a gap. And as we tune the qubit into the gap, you have this photon-bound state. Okay. And one of the things that so this talk sort of explores one of the topics they mentioned in the end of that paper. Okay. So what we're going to do is start with our sort of favorite open quantum system. So what this consists of is our qubit that's completely resonant with the cavity. So here's the energy levels of my qubit, and I'll set it up to be resonantly coupled to the cavity, resulting in these hybrid light matter states, our polariton qubit. And the advantage of this is I can create a system where the decay of these energy levels is completely dominated by coupling to this single mode of the environment. That is, I can make a very much a one-dimensional atom. All the light goes out exactly one mode of the mirror. And we often use this as a resource for quantum measurement. Now we can detect this field and determine what the quantum state of this system is doing. But in this time, what I'm going to do is alter the medium into which this decays and see what that gives us. Okay, so we have an effective two-level system that radiatively decays in the environment, and you can think of it as just fluorescing, and we might measure the fluorescence with a detector. Okay. So what I want to do is take my cavity QED system, I'll make one mirror more transparent than the other, and allow it to decay into an environment that's one of these photonic media. And see how, as I bring the edge of a band into resonance with the atom, what kind of physics I get. Okay? And the implementation with circuits is quite simple. We take our cavity, which we've configured to be roughly in resonance with our qubit, and we simply couple this to a modulated impedance waveguide. So it's as simple as I've shown here. It's a coaxial cable that we've rippled in a certain way to create bands and gaps. It has a 50 ohm, 30 ohm stepped impedance. So this is actually a common technology. This is what we call a stepped impedance filter. So if I measure this filter transmission just at room temperature, here's what I see. I see a region where the transmission is very low. That'd be a gap. See the place where the transmission is roughly unity. That's the band. And there's some funny features having to do with the specific length of the filter and the depth of the modulation and so forth. Okay? So I'll set this up as the environment for my qubit. And so here for reference is the cavity resonance. And so as I change the frequency of the qubit relative to the cavity resonance, the degree to which the hybrid states are cavity-like or qubit-like varies, leading to a Purcell enhanced decay close to resonance of the cavity and suppressed decay farther from the cavity. Okay. So taking these two pieces together and snapping it together and cooling it down in the dilution refrigerator, we find that over some narrow region, there's a place where the decay rate can vary by over an order of magnitude. So here's the decay rate measured just the inverse lifetime of our qubit as a function of frequency, and we see this very sharply spiked decay right here. So I might call this my band and this my gap, if you like to use this language. Okay, so let me give you an example of what can be done with such a strongly varying decay rate of our qubit. Okay, so this is a bath engineering. So the idea is what I'm going to do is I will drive my qubit on resonance. So this is just a resonant drive on the qubit. And what this resonant drive does is in the frame rotating with the drive, we have these dress states dressed by the drive. And we end up with states, okay, so here are the eigenstates of the system. N minus 1 photons, some eigenstate plus, that's the eigenstate of this drive operator, and n minus 1 photons minus. And then up here, a drive frequency away, we have n photons minus n photons plus. So these are the dress states of the system. And the spontaneous emission of this in this case here is given by the Malo triplet spectrum. Okay, those correspond to transitions from plus to plus. That's the green one. That's the resonant transition. And then we have this minus to plus transition, which is blue shifted by the Rabi frequency. And we have the plus to minus transition, which is red shifted. And the idea here is just to put one of these sidebands into the band, and the other ones are in the gap. So I'm therefore suppressing some transitions while enhancing other transitions. What you can see is what this will do is the dissipation into this now non-uniform environment will favor one of these states over the other. So in this case, it favors the plus state because it can decay into this state, but it won't decay from the plus state into the minus state. So another advantage of these superconducting qubits is that we can very efficiently and robustly measure the state with quantum state tomography. We just measure the state, and in combination with rotations, we can determine all the expectation values of the Pauli matrices. So for example, here's just simple Rabi oscillations, just from time 0 to 100 nanoseconds, and you see oscillations in the z-y plane due to the drive along the x-axis of the qubit. But if we wait long enough, what I find is it's no longer oscillating, but instead is it generated sort of a steady state coherence along the x-axis. So it's entered into favoring one of these eigenstates of the drive over the other. That's the essence of this path engineering. So we can actually change all of the parameters in the system. We can change the detuning here and the Rabi drive strength and sort of map out what are the steady state, what's the steady state of the system given these drives decaying in this environment. So you can see on resonance, we see as you increase the Rabi drive frequency, we're now making a bigger difference between the blue and red sidebands of the Mallow triplet, thereby favoring one of those states over the other. So you see an increase in the x component of the qubit, the expectation by sigma x. But you can also see as you go off resonance, what we have is where the eigenstates are now tilted from the equator of the Bloch sphere. Okay, so we'll have eigenstates that are closer to the ground state or closer to the excited state as we alter from positive to negative detuning. Okay, so this, again, as I said, a work in progress, studying how this non-uniform density of states in the environment can be used to control the quantum state. So as an outlook, it would be interesting to study the multi-qubit case. So you can imagine now putting 2 or 3 or 4, maybe not very many more than that, qubits in this cavity and using this a combination of drives on the system and this environment to now generate entangled states of the qubit. So this has been done just using the cavity density states to sort of laser cool this into certain entangled states, but the same ideas will apply in this case here. Another idea we have is we can start to create different photonic media to connect to this cavity. We can apply as many connections to this as we like, and we can have some of them have different bands and gaps in different areas. So you can think about creating things that are, in some sense, similar to p-n junctions with this photonic media. And then ultimately, we can have many of these qubits, many cavities hooked up in quantum networks, but now where we're controlling, in some sense, what frequencies travel in which directions. So that's my outlook for this. And with that, I'll thank you for your attention and show a picture of my group being silly. So thanks.
Is it obvious that the sort of Zener effect you're talking about is the same as Zener effect we're hearing about this morning? Because you're doing some like pretty golden rule-like stuff where you're moving your frequencies around and like messing with where you sit at the back spectrum, whereas there we're talking about sort of repeated, rapid, hard measurements. Right?
Yeah. So is it obvious that they're the same? I don't think that's. No, I don't think so. But I think the way to think about the xenodynamics is you have a manifold of states, and by measuring it, you sort of introduce either a gap or you introduce some dephasing on a state, allowing it to, confining it to a certain manifold of states. So maybe that's and that's like one consequence of this sort of measurement is you're confining these dynamics. Here, I guess, is a separate consequence of the two, where we were constantly dephasing the states, perturbing how it couples to the bath. So I guess they're fairly separate things, but they both, at the core, have to do with dephasing of a certain transition, a certain state, and preventing dynamics, and that's what's similar.
Specifically, like, you know, we heard about how you can just like block certain states from being populated altogether, and it's not sort of obvious you can do that by just adding unitaries as opposed to adding measurements. Well,
I think you can do that fairly well by adding unitaries in the case of xenodynamics. Say, for example, you apply a drive on a certain pair of states and you split those drives, but to some extent bringing them off resonance with some drive. And that's an example of xenodynamics. The people who are really picky about the community reserve the word xeno for having to do with dephasing associated with measurement. But you can certainly, and in this case, we could also change the effective decay rate by just applying a unitary drive on the qubit. That splits the spectrum, it samples different parts of the bath in a way that's similar to the bath engineering experiment. So whether or not we should call that the Zeno effect or not is, I think now it's just a semantic question.
Quick question about these modulated impedance waveguides. Are
Yeah.
they lossy? In other words, is there another path that one has to take into account?
They are, the amount of loss in what in our case is maybe 20 or 30 centimeters of cable is negligibly small. It's copper, it's at very low temperature, so it's quite low loss. And you can certainly imagine making these waveguides out of a superconducting material and make an actual true waveguide, in which case it wouldn't be very lossy. Are there losses in these systems? Yes, there are lots of losses in the systems. But actually in this implementation here, we're actually avoiding any of the things that are truly lossy in these quantum circuits everything here can be a superconducting material, quite low loss compared to when we say, for example, want to measure signals, we have to send it through a circulator, which is a really lossy material. So we generally don't have to worry about the loss in this case any more than usual. So no more than usual. Yeah.
Is that what limits the T1 contrast? Residual loss? No, just something else.
Oh, I think what limits the contrast we see, so the residual loss we have is lossy. So our qubit here has some maybe decay into other channels, decay due to impurities in the junction, due to various other things. So the level to which we can make our quantum systems very lossless is limited at the moment. It's an order of magnitude, maybe 2 orders of magnitude better than it was when I started in the field, but it's still not perfect. As I said, the typical lifetime of these in our lab is maybe tens of microseconds, and we could increase the decay rate by coupling this environment by an order of magnitude above that. That's kind of the level at which we can work now. But you can imagine making it more strongly coupled to the environment to increase that decay rate, for sure.
So the zero effect, so what was the bandwidth of your reservoir compared to the other
Yeah.
constants?
Okay.
Of the dynamics?
So the bandwidth of the reservoir was, in order for it to see appreciable effects, the bandwidth of the reservoir should be on order similar to the bandwidth of the measurement, the rate of the measurement. So the spectrum we created had a roughly 1 or 2 megahertz bandwidth. And our measurement rates of 1 or 2 megahertz was able to therefore appreciably change the decay rate by a factor of 2 or something. So that was the frequency range bandwidth we chose.
Which is there below the coupling between the qubit and the microwave.
And so in that experiment, we were working in this. The qubit was dispersively coupled to the cavity. So the dispersive coupling that rate in that case was actually smaller than that, something like a few hundred kilohertz, meaning that we had to send in, if we want to make these projective measurements in 100 nanoseconds, we'd send in roughly 10 photons to get an appreciable measurement rate that we could, in principle, measure the state in 100 nanoseconds. But yeah.
So in a naive approach, if you're on the slope, it's very steep spectral function to the path, the effect is rather light shift or some frequency shift than a decay.
Oh, okay. So good point. So you're saying that here we are on the edge of this thing, and as you send in photons, you're actually going to Stark shift the qubit, and that'll cause it to sample more or less of the bath. And that would lead you to therefore think that that you'd observe these effects. So the advantage of the quasi-measurement test is there's no light shift on the qubit at all. You could see that its spectrum stayed at the same time, but you could see when we were making the actual dispersive measurements, there was an overall shift of the frequency, which basically just shift the frequency of the qubit relative to the bath, and that's actually something we can correct for and just shift the measurement over to compare like frequencies. So that's something we can take into account, but also something that we can eliminate by using these quasi-measurements. All right.
There's just one aspect of this resonance fluorescence I didn't understand, so maybe you could at any time. Normally, not only do you get a sort of central side band when you get two peaks, but there's also photon correlation. So there's always a red photon with a blue photon. They always come in coincident pairs. So when I do reservoir engineering to suppress one, there seems to be an inconsistency. How can it,
Well, I mean, you can imagine. I don't. Well, I guess I don't understand that they had to come in pairs.
It's because if you go into as long as you're not power broadened, you go to the weak intensity limit, and you look at this thing you showed, like plus to minus and then minus to plus.
Yeah.
If you go through those cycles, you sort of realize that there has to be a big one with every small one. And so if you do an experimental measurement and look at the coincidence, you always see a photon in each of the side bands.
Very interesting. I can imagine that would be really interesting. So you could imagine.
But maybe the reservoir engineering
breaks the symmetry there.
I'm sitting on the energy shell when I talk about that argument.
Yeah.
I don't know.
I mean, so in this case, you can imagine you suppressed from scattering one of those photons and the other, so you'll still have the central peak, the one. But then looking at the correlations of the output fields as we've broken the symmetry could be an interesting, a worthwhile project. So I'll take that under consideration.
Don't you end up with the same correlation, except the second proton comes out with a long time delay, which means you're dwelling in this state, but essentially your optical population.
Ah, there you go. Yeah. Because those photons aren't completely
You get frozen for a while before the second one comes out.
prevented.
Integrated the area of it, the two sidebands with the total number of photons in each. It seems
Yes.
impossible.
Because you can't pump a second one of the fast decaying photons out until the first one comes out. So you sort of
That's
run
right, yeah.
average